All right, welcome to the videos for section 6.5. In this section, we're studying the idea of the average value of a function. To get us started, we want to start with the non-calculus idea that we're basing this on, the average value of a set of numbers. So if you have a set of numbers like this list that I've got right here, 1, 3, 3, 5, 8, and you want to find the average value of this set of numbers, we have a common strategy for that. What we do is we add up all the numbers in the list and we divide that value by how many total numbers there are in the list. So in this case, the average value is going to be what we get when we take 1 plus 3 plus 3 plus 5 plus 8 and divide the whole thing by 1, 2, 3, 4, 5 total, since there are 5 items in the list. So when we add this up, 1 plus 3 is 4, plus 3 is 7, plus 5 is 12, plus 8 is 20. So we get 20 divided by 5, which is precisely 4. So we would say that the average value of the numbers in this list is 4. Okay, so let's see if we can take this strategy here. By the way, another name for this is the arithmetic mean. So if you're a statistician or concerned with statistics at all, this phrase should mean a lot to you. All right, so how can we extend this idea of an average value to something like a function? Because with a function, we're typically talking about an infinite number of function values, right? We can plug in an infinite number of values into the domain and get out an infinite number of values in the range in most cases. So how can we talk about an average there when we can't count the number of things in the list, right? When it's an uncountable number like infinity. How do we do that? Well, here is our basic idea. And this is going to sound familiar if you think back to the other applications we've had for integrals so far. We are going to take the function and we are going to split it up into a finite number of pieces. A finite number of pieces, each of which is going to be a short interval. So for example, just draw a picture here real quick of a function. Imagine that I'm trying to find the average value of this function from the left side to the right side of what I've drawn here. Well, one way that I can do that is I can take the interval on the x-axis here, and I can split it up into a bunch of subintervals. All the way out to here. There we go. So we split this up into a bunch of subintervals, and then I pick one specific point from each one of those subintervals and find the corresponding y value. So this value here we could call y1 to correspond, so there's y1, to correspond to the value down here, which we would call x1, the first tick mark after the left side, right? So we've got x0 on the left, x1, then x2, x3, all the way up to xn on the far right side. So in the first subinterval, we pick one particular point, and we can call it y1 or y1 star if you like. Then we do the same thing for each of the other values for each of these other subintervals here. In each one of the subintervals, we pick a single point out. So maybe here, and then maybe here, and then here. Pick one over here. Pick one here. One for each of the subintervals. There we go. So that if you have n total subintervals, you get n total terms, or n total y values up here. So here's y2 star, all the way up to yn star. So if you look, you can now add up a finite number of y values, and each one of those y values is going to approximate the average for that little range there, right? So take a look at one particular subinterval from here to here, for example. We are going to assume that this y value here is approximately the average within this little subinterval. And so the average of all of these little averages is going to be the overall average value of the function. That's kind of the idea that we're going for here. So what does that look like? Well, it means that I need to add up all of these y values. So we'll have y1 star plus y2 star plus y3 star plus all the way up to yn star. And then we divide that sum by the total number of values in that set. In this case, just n. Just divide by n. Okay, so this is our approximation. Again, this is just an approximation for the average value of the function. Now we can rewrite this in a couple of different ways that are important here. First of all, each one of these y values, if you track it backward down to the axis down here, right? Pick any one of them and track it back down to the axis, you are going to find that there is a particular x value that goes along with it. So here, this one would have been y4 star. So let's call the value that matches to it, the x value that matches to it, x4 star. And in general, if you look at the ith element here, call it yi star, it matches back to one specific x value, which we are going to call xi star, right? You can take any of these y values and find an x value that map to it. That's the goal here, right? That's how a function works. So that means that each of these y values is now the function output of a corresponding x value. So I can rewrite the numerator of this expression as f of x1 star plus f of x2 star plus etc., all the way along to f of xn star, all the way at the end. So we have the sum of the function values where each of the inputs is from those subintervals. And instead of writing n in the denominator, I'm going to make the following little algebraic substitution here. Again, we have these n subintervals here. We're going to call the length of each one of these subintervals delta x. So if you measure from here to here, you get delta x. And as usual, delta x is equal to b minus a over n, where b and a are the endpoints of my interval here. So xn is equal to b, and x0 is equal to a. The far left endpoint is a, far right endpoint is b. So if you need the length of one of these subintervals, take the entire length from a to b and divide it up into n little subintervals. So this is our familiar equation here. I'm going to solve this equation for n. So multiply both sides by n and divide by delta x. You get n is equal to b minus a divided by delta x. So I'm going to make this substitution as well. The denominator here should be the fraction b minus a over delta x. All right, now we can rewrite this again. When you divide by a fraction, we can keep it, change it, flip it. This should sound familiar from algebra. We're going to flip this fraction upside down and multiply instead of dividing. So we are going to now get this fraction flipped upside down means that we'll have a delta x in the numerator along with these function values. So we are going to have f of x1 star plus f of x2 star and so on, all the way up to f of xn star, all multiplied by delta x. And then in the denominator, we now just have b minus a. And in many cases, people like to just factor that fraction out, so we would have a 1 over b minus a out in front. Okay, so far so good. I have defined an approximation for the average value of my function, and I've rewritten it in other terms. So what do we notice here? Well, you might notice that if you look at the bracket here, you have a function depending on a bunch of different values of the, you have a sum of a bunch of different function values, all added up together, and each one of those is being multiplied by delta x. So instead of writing it that way, I might instead write 1 over b minus a times the summation from I equals 1 to n of f of x I star multiplied by delta x. And if we wanted to make our approximation better, I don't know how many times I've said this so far, it's the same idea as we've been using in all our other applications, right? We have an approximation, we want to make it better, what do? We make n larger, meaning we're shrinking delta x down towards 0. As n increases, we should have more and more sample points, right? And the more sample points you have from along this curve, the better your approximation is going to be for the average value. And, as you might guess, if you apply a limit here as n goes to infinity, that approximation should go to some particular value, which will be the true average value of the function. The limit should approach the true average, even though none of these actually takes into account all of the points. So, when we apply a limit to this with n going to infinity, we will get the true value of the average value of the function. So what does that look like? Go back up here, I guess. This is where I wish I had 2 chalkboards. All right, we'll come back up to the top. So now the true average value is going to be equal to the limit as n goes to infinity of this expression here. So we have 1 over b minus a multiplied by the summation from I equals 1 to n of f of x I star times delta x. Okay. And we know that any time we have a limit as n goes to infinity, where we have a summation of a function value times a number that's shrinking towards 0, that is the definition of a definite integral. The 1 over b minus a is actually a constant, right? For this particular problem, b and a should be fixed values. We're looking at a fixed interval here that we're trying to find the average value on. So this is just a constant and can be factored out completely. And so we will get 1 over b minus a multiplied by the integral now from a to b of our function f of x dx. Right? The limit of the sum of f of x I star times delta x just translates into that. So the average value of a function means, first of all, take the integral of the function over the interval that you're interested in, and then divide it by the length of the interval. Right? B minus a here is just the length of the interval. So, why does this make sense? Well, remember that we're talking about the average value of the function. That means the average height, right? The average y value. This is a one-dimensional measurement of length, right? So we are asking a question about length. So how do we get that? What you do is you take an area, right? This expression right here is an area, and you divide it by its width, right? Take the overall area and divide it by the width. You're going to get the average value of the height. That should make some intuitive sense there too. So this formula right here, the average value formula for the function, is what we're going to be using throughout this section. And in the next videos, we're going to see some examples of how to use it.